Hey guys, welcome to this video on Laurin Series. So, just like I said in the last video, Laurin Series is a special form of the Taylor series that is centered at x is equal to 0. So, recall that from the Taylor series, we have that f of x is f of a plus f prime of a multiplied by x minus a plus second derivative of a divided by 2 factorial multiplied by x minus a squared plus um, and get to the nth derivative divided by n factorial multiplied by x minus a raised to the power of n plus the other terms. So we know that f of a, if we shrink it down using the summation notation, is this. So now, since we said the Maclaurin series is a special form of the Taylor series that is centered at a is equal to 0, so when a is equal to 0, we have that f of x will be equal to f of 0 plus f prime of 0 multiplied by x plus f prime prime of 0 multiplied by x squared divided by 2 factorial plus goes on like that fn of a divided by n factorial, sorry, not a is 0, multiplied by x raised to power n plus the remaining terms, and this gives us an infinite summation of fn0 x raised to power n divided by n factorial. So this is the Maclaurin series for the expansion of a function. So let's take a look at a question to explain this concept. So this question says we should find the Maclaurin series expansion of sine e raised to the power of x. So let's apply the Maclaurin series to solve this question. So to do this, let's take a simpler case. Let's consider the expansion for sine t. So if we have a function f of t be equal to sine t, then it means f of 0 will be equal to 0, then f prime of t will be equal to cos t, and that means f prime of 0 will be equal to cos 0, which is equal to 1. So on evaluating the second derivative, you have f prime prime of t to be equal to minus sine t, and f prime prime of 0 is equal to 0. Same thing for the third derivative. We have minus cos t, and at x is equal to 0, you have the value as minus 1. The fourth derivative follows through, and that becomes sine t once again. And at t is equal to 0, sorry, we have this to be equal to 0. We evaluate the fifth derivative, you can see that this becomes cos t, and at t is equal to 0, we have the value as 1. Therefore, we can write our expansion for sine t as 0 plus t plus 0 minus t raised to the power of 3 divided by 3 factorial plus 0 plus t raised to the power of 5 divided by 5 factorial plus 0, then minus t raised to the power of 7 divided by 7 factorial, and it goes on like that. So on simplification, f of t becomes t minus t raised to the power of 3 divided by 3 factorial plus t raised to the power of 5 divided by 5 factorial minus t raised to the power of 7 divided by 7 factorial plus the rest of the terms till infinity. So since we need the expansion for sine e raised to the power of x, we can substitute e raised to the power x for t to obtain our expansion for e raised to the power of x. So this means that f of x is sine e raised to the power of x, and this now becomes e raised to the power of x minus e raised to the power of 3x divided by 3 factorial plus e raised to the power of 5x divided by 5 factorial minus e raised to the power of 7x divided by 7 factorial, and this goes on till infinity. Now let's consider g of x to be equal to e raised to the power of x. It means that the first derivative of x is equal to first derivative of g with respect to x is equal to its second derivative, which is the same thing as the third derivative, and it goes on, and this is still going to be e raised to power x. Therefore, this means g prime 0 is equal to g prime prime 0, same thing as g prime 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 0, and is equal to the rest of the derivatives, which is equal to e raised to power 0, and that's 1. We can therefore write the expansion, Maclaurin series expansion for e raised to power x to be equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial and it goes on like that till infinity. The reason why we are doing this is because we can't leave this as e raised to the power of x. The objective of using the Maclaurin series is to get a polynomial expansion for any function that has derivatives and is also continuous. So in this case, we substitute the value of e raised by x into the function that we have here. So now f of x is sine e raised to the power of x, which is now equal to 1 plus x plus x squared divided by 2 factorial plus x raised to the power of 3 divided by 3 factorial plus the rest of the terms till infinity. Then plus, when you substitute the one for e raised to the power of 3x, we now have, we substitute 3x in place of x, 1 plus 3x plus 3x squared divided by 2 factorial plus 3x raised to the power of 3 divided by 3 factorial plus the rest of the terms till infinity divided by 3 factorial. So this should be negative. Then to the next term, which is 1 divided by 5 factorial multiplied by 1 plus 5x plus 5x divided by 2 factorial is squared here, then plus 5x raised to the power of 3 divided by 3 factorial plus the rest of the terms up till infinity. Also here, it should be 3x all raised to the power of 3. So this is going to be the polynomial expansion or the Maclaurin series expansion for sine e raised to power x. But you can simplify this further by grouping the terms with the same power. You can see that here we have terms in x squared, we have a constant term and the other powers. The same thing applies here and in this third expression. Therefore, we can group them together. On grouping them together, let's say the constant terms first, we now have 1 minus 1 divided by 3 factorial plus 1 divided by 5 factorial plus the rest of the terms, then plus the terms for x, 1 minus 3 divided by 3 factorial plus 5 divided by 5 factorial plus the rest of the terms. We also consider for x squared, we have plus x squared divided by 2 factorial into brackets one minus 3 raised to the power of 2 divided by 3 factorial plus 5 raised to the power of 2 divided by 5 factorial plus the rest of the terms. and this goes on for the other terms too. So if you take a look at this first term here, it is equivalent to the value of sine 1, because we already stated that sine t from the expansion we made before, that sine t is equal to t minus 3 raised to power 3 divided by 3 factorial plus 3 raised to power 5 divided by 5 factorial minus 3 raised to power 7 divided by 7 factorial, and so on. So substituting t is equal to 1, we have that 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, and so on, will give us the expansion for sine 1, which is what we are having here. Then for the terms in x, if you look at the terms in x, you have that this can be simplified to give 1 minus 1 over 2 factorial plus 1 divided by 4 factorial plus the rest of the terms to infinity. And on the expansion of cos t and substituting t is equal to 1, you have that this is the expansion for cos 1. So that's the second one simplified. We can now write the remaining terms in x squared, x cubed, and so on using the summation notation. So using the summation notation, we can see that if we go back to what we've gotten here, you can see that the next term in this expansion is going to be x cubed divided by 3 factorial multiplied by 1 minus 3 raised to the power of 3 divided by 3 factorial plus 5 raised to the power of 3 divided by 5 factorial. Then it goes on and on like that. That's the way the steps follow. The same thing goes for x raised to the power of 4 divided by 4. It becomes 1 minus 3 raised to the power of 4 divided by 3 factorial plus 5 raised to the power of 4 divided by 5 factorial, and so on. So since we can see that there's a trend there where the powers are increasing progressively, the powers of the outside polynomial, for instance, in the case of x raised to the power of 3 now, divided by 3 factorial, we have the expansion inside to be 1 minus 3 raised to the power of 3 divided by 3 factorial plus 5 raised to the power of 3 divided by 5 factorial minus 7 raised to the power of 3 divided by 7 factorial, and it goes on and on like that. For x raised to the power of 4, the same thing follows. 1 minus 3 raised to the power of 4 divided by 4 factorial plus 5 raised to the power of 4 divided by 5 factorial minus 7 raised to the power of 4 divided by 7 factorial plus the rest of the terms. So this continues on and on till infinity. Now we can see that only the powers on the outside polynomial and the powers of the constants inside the parentheses are increasing. There's a constant of 1 minus 3 plus 5 minus 7. So we can see a pattern there, and thus we can write them in terms of summation instead of writing all the way till infinity. So taking a look at this, the rest of the terms can be written as this. We know that x raised to the power of n divided by n factorial is constant because n is increasing from 2 and it goes on it gets to till it gets to infinity. So we can say this is a summation from n is equal to 2 to infinity. Now for the inside values here, sorry, there's a mistake somewhere here. This should be 3. So we can see that we have 1, 3, 5, 7. We can write that as a we can write that as a geometric or an arithmetic progression. So using the main ideas from arithmetic progression, we can represent this as 2b plus 1 divided by 2b plus 1 factorial, where b is starting from 0. But that's not just enough to describe it. We can also notice that the signs interchange from negative to positive, negative to positive. So we can also incorporate that by adding a term minus 1 raised to the power of b. So this means if we make a summation from b is equal to 0 to infinity, we can represent adequately what is happening within these boxes for each of the polynomials. So this gives the shortened version, or in terms of the summation notation, for the rest of the terms. And because of this, we can write the expansion of sine e raised to the power of x as sine 1 plus cos 1 divided by 1 factorial plus the double summation that is representing the rest of the terms. N starts from 2. Then there's also a summation for b is equal to 0 till infinity of x raised to the power of n divided by n factorial multiplied by 2b plus 1 divided by 2b plus 1 factorial multiplied by minus 1 raised to the power of b. And this gives us the expansion for sine e raised to the power of x. And with this, we've come to the end of this video on Laurin series. See you guys in the next video when we'll be talking about the applications of differential equations starting from L'Hopital's rule.